Hi, everybody, and welcome back for Activity 16. So Activity 16 is called More About Quadrilaterals. So in this activity, each section is kind of dedicated to proving that different quadrilaterals are specific shapes. So in today's lesson, 16.1, we're going to be proving that a quadrilateral is a parallelogram. So we're in our Springboard books, page 223. So open that up, and we'll get started. Okay. So in a previous activity, we learned that the definition of a parallelogram was used to verify, okay, we verified this by showing the opposite sides are parallel. That's how we get its name, parallelogram. So what we're going to do is we're going to start by looking at quadrilateral chia, C-H-I-A, and we're going to find the slopes of each side. So you're going to find 4 slopes here. So find the slope of CH and AI. Same thing with CA and HI. So go ahead and find those slopes, and we'll talk about what that means after. Okay. If you did it correctly, you should have got that HI and CA had a slope of 0 because they both just are straight horizontal lines. CH and IA both had a slope of 5 halves. Now, what we know about slopes from Unit 1 is that if we have the same slope, we can imply that we have parallel lines. We'll just make some little parallel marks on our picture here. Okay, so we can use slopes to verify that something is a parallelogram, okay, by showing that they're the same slope on the opposite sides. All right, let's look at quadrilateral skip. It says that SK is perpendicular to IP, or sorry, not perpendicular, they're congruent, they're equal. And we also know that KI is equal to SP. Now, what else do we know is congruent in this picture? What else can we assume? Okay, well, we can assume our reflexive property here. So SI is congruent to itself. So we can't say that triangle PSI is congruent to triangle KIS, because if we look at our markings here, we have side, side, side. Okay, well, then that means we can imply that different angles are congruent as well. So SIP would be congruent to angle ISK, and PSI would be congruent to angle KIS. And why can we say that those angles are congruent? Well, if we proved congruent triangles, we could use CPCTC, our good friend here. Okay, so looking at those angles here, so we have SIP, so that angle is congruent to ISK. Okay, and we also have PSI congruent to KIS. Okay, so if you're looking at our markings there, it's not the neatest picture, but looking at those markings, those are alternate interior angles. Okay, so these lines are parallel to each other because alternate interior angles, if those are congruent, then that implies that we have parallel lines. Okay, so we can prove that this quadrilateral is a parallelogram because we proved congruent triangles, which helped us prove that angles were congruent. And if we have alternate interior angles that are congruent to each other, that implies parallel lines. That's from our last unit as well. Okay, so here's our first theorem. It says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Here. I always spell this word wrong, but get better. Parallelogram. Oopsie, I did spell wrong. There's no one there. All right. Okay, so that's your first theorem. So if you have pairs, opposite sides that are congruent, you can prove that something is a parallelogram. Okay, let's just jump to the next page here, number 4. Same thing, we have a picture here, quadrilateral WXYZ. They're telling us that we have some parallel lines. So WX is parallel to YZ. And they're also saying that those are congruent. Let's make our little congruent marks as well. So they're parallel and congruent. So if we know that they're parallel, again, we can have our alternate interior angles, right? We can assume that. We can also assume a reflexive property there, W or ZX congruent to itself. So I can say that these triangles are congruent. WZX would have to be congruent to triangle Y XZ. because if we have a side, an angle, and a side, we can prove congruent triangles. Okay, so then why can we say that WZ is parallel to XY? Okay, kind of a similar idea with the last page, but we can say that these lines are parallel because if those are congruent triangles, CPCTC allows me to say that these alternate interior angles are also congruent. Okay, so again, alternate interior angles, if they're congruent, we can imply parallel lines. So here's our next theorem. If one pair of opposite sides of a quadrilateral are congruent and parallel, then we can say that that quadrilateral is a parallelogram. Okay. So again, if you have one pair of opposite sides that are congruent and you know they're parallel, all those other things kind of get put into place automatically. So if we have one congruent side that is also parallel, we can just imply that it is a parallelogram. Okay. All right, let's now skip to the next page. Let's go to problem 6. So down here. Okay, so we have a quadrilateral plan who has diagonals PA and LN, and those diagonals bisect each other. So if they bisect each other, that means it cuts it in half. So we can make some markings here, some congruent markings that we can imply. Okay, so they're saying we can prove some congruent triangles here. We have triangle LEP. They're saying is going to be congruent to triangle NEA. Now, what can we assume in this picture that can help us prove those two triangles are congruent? Well, hopefully, you are looking at those vertical angles. Remember, we can use vertical angles to imply, if they're vertical angles, we know they're congruent. So we can say that is congruent to each other by side, angle, side again. Same thing with triangle LEA. We could say that that's congruent to triangle NEP for the same reason. Okay, these vertical angles are also congruent to each other. So side, angle, side again. All right. So again, this is all kind of similar every time, but we can also prove our angles here. We have angle ALE is congruent to angle PNE. Same thing with ELP is congruent to triangle or angle ENA because of our friend CPCTC. Okay, so again, we can imply if we have alternate interior angles, we could say that they are parallel, leading us to our last kind of theorem here. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Okay. All right. So those are your three theorems. So if you know the diagonals bisect each other, we could say parallelogram. If we know we have one pair of opposite sides that are congruent and parallel, we could say it's a parallelogram. And if both pairs of your opposite sides are congruent, we can also say parallelogram. Okay. So let's just kind of finish this up here. So we have given this quadrilateral thin, THIN. There's the coordinates for those. They want you to find the midpoints for those diagonals. So in the diagonals, if we have this quadrilateral, THIN, the diagonals would be TI and HN. So I'm going to have you guys go ahead and find the midpoint. If you don't forget, remember midpoint is the average, okay, of your coordinates. So x1 plus x2 divided by 2. Same thing with your y's. So find the midpoints of TI and HN for me really quick. Okay, so what I got for these is, here's my work. I'm just going to pull it out here. So I got that their midpoints were 4.5, so 4.5, comma 4. So So what that tells us then, that the angles do bisect each other because they have the same midpoint. So their middle is the exact same on each line. So if they both have are points, okay, at the same midpoint, then that means they're bisecting each other. They're both passing through the same point as it's being cut in half. So if we were to describe this, we prove that their diagonals bisect each other. So that is a way that we could prove that something is a parallelogram. Okay. All right, we're just going to finish this lesson up with some practice problems on the last page, and then we're done. So let's look at these here. So in 11 through 14, we're going to look at the picture and tell what theorem can be used to prove that the quadrilateral is a parallelogram. If there's not enough information, okay, then you'll just say you can't do it. So if I look at 11 here, so they're marking some parallel lines, and they're marking some diagonals. So from this picture, can we prove that this is a parallelogram? Does it fit any of our theorems? Oh, actually, this one, no. Okay, so we have to know, if we know parallel lines, we would also have to know that those parallel lines are congruent. They didn't tell us that, so we don't know that. And the diagonal, one of those diagonals is being bisected. We can see by the tick marks here. But in order to be a parallelogram, they have to bisect each other. So again, I would have to know that those, okay, are also congruent in order to prove a parallelogram. So not enough information in number 11. Let's look at number 12. Can we prove that this picture here is a parallelogram? Okay, so for this one, the answer is yes. Okay, because they're showing here by their tick marks that their opposite sides are congruent. Okay. And that we know is a property of parallelograms. If you remember from the notes that we did in class today when we filled this out, opposite angles are congruent. That is a property of a parallelogram. So we can use that to prove that actually is one. Okay. Let's look at 13. Can we prove that 13 is a parallelogram? Okay, again, this one would be a yes. They're showing that those diagonals are in fact bisecting each other because both have those little tick marks, congruent tick marks. Okay. And lastly, this picture number 14, they're showing parallel lines and they're also showing congruence. So that would also be another way to show you that that is a parallelogram. That's your second theorem that we went through. Okay, so I'm going to go over 15 because there's no problem like this really in the book, but we're giving 3 vertices of a parallelogram and we have to find the 4th one. So I'm going to do 15 for you and then you guys can try 16 on your own. But I'm going to plot these points. It's easy if you have a graph, so if you want to draw one in for yourself on the side here, it'll be helpful, but 1, 2, 3, 4, 5. So there's 1 point. Then we have 3, 3, and 8, 3. 1, 2, 3. So there is our parallelogram. So those are 3 of the vertices, but we need to find where the 4th one is going to be located. So we just kind of put in some lines here. Okay, so remember, if they're a parallelogram, their opposite sides have to be congruent. So you can either figure out how long this point is, and you can make that length. So in that case, you might have to do like distance formula or something. But it might be easier if we just use the straight side. That has a distance of 5, if I counted that correctly. Okay, so that means your top part of your parallelogram, if it's a parallelogram, the opposite side has to be congruent. So if the top part would also have to have a distance of 5. So 1, 2, 3, 4, 5. So that means this would be my parallelogram. Okay. So where is that 4th vertice then? Let's count. So that was at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So it's 6, 5. Let's see if I got it right. I did. Okay, so I'm going to have you guys try 16. Draw a new graph if it helps you out. I think it just visually is a lot easier to try to do it that way because I can just kind of count that on my graph. But go ahead and find the 4th vertice for 16. So the 3 points are there. You're going to find the 4th one. Okay, if you did it correct, it should have been at 6, -4. Okay. All right, so that is our first section of activity 16. So again, proving something is a parallelogram, you can use bisecting diagonals. They have to bisect each other. We could also say it's a parallelogram if you have one set of congruent parallel sides, opposite sides. And we can also say something is a parallelogram if we know that the opposite sides of the quadrilateral are congruent, that both pairs of opposite sides are congruent.